Hi, my name is Catriona. I'm currently a postdoc at the University of Edinburgh working with Ed Silson, and this is work that I did while I was a postdoc with Alexandra Walger at the CBU in Cambridge in collaboration with Teal Grootswagers at the University of Western Sydney. So the question that we had was, how can we best help our multivariate classifier in distinguishing between effects within our data? So just in this toy example, you can think of a classifier as trying to best separate two sets of data from two different conditions shown in the different coloured dots here. And it's attempting to find a way to separate those in the most optimal way. And then what you do is you apply that separation from the classifier on some unseen data as shown on the right. And you look at how often, depending on the number of trials that you have, how often it will accurately classify them into the correct condition. But the question is, will our classifier perform better if we have fewer but stable estimates of activity, so for example by averaging over trials, or by providing it with more but noisier trials, so just giving it all of the single trial data rather than averaging? Will that perform better than if we give it fewer averages over our trials? And of course, it's not always intuitive when you start analyzing your data or before you collect your data, which of these will be optimal for your particular experiment or your particular classifier. So to answer this question, we simulated some data using Cosmo MVPA, where we simulated two conditions with a medium effect between them, and 90 trials across 3 separate blocks so that we can do threefold cross-validation, 100 participants or data points, and we tested a couple of different classifiers that are commonly used. I'll just orient you to the graph that I'll present many times during this presentation. On the left y-axis, we have our decoding accuracy, so that's the percentage, the number of times that the classifier accurately separates our conditions. On the right-hand y-axis, we have our t-score, so that is just the t-test against chance for each of our mean decoding accuracies, and chance level in this case being 50% because we had two conditions. And on the x-axis here, we have the number of trials per average. So that is just the number of trials that we included in our pseudotrial or our average set of trials. What we can see here, if we plot the very first bar, each data point here is a subject. And you can see that if we don't do any averaging, we don't create any pseudotrials, with our naive Bayes classifier, the mean accuracy is around 55%, and we have a t-value of 11. So actually the coding is okay, it's fairly good in this instance. Then what we can do is add more points to our graph. So what you can see here is there's an immediate improvement in the t-score, even by just increasing the number, well, by starting to average your trials together by using averages of 2. And essentially this continues, you continue with this improvement until you get to about half of the number of trials available. What you see then, particularly with this naive Bayes classifier, is a sudden drop-off in the performance of the classifier, such that our decoding accuracy has now dropped dramatically, as has our t-score. So the naive Bayes classifier really struggles once you are only giving it one trial per block. So in this instance, the naive Bayes classifier seems to prefer more noisier estimates than fewer, more stable ones. And just to point out why this is happening, of course, when we do no averaging at the start, we have 90 trials per condition. Then when we start averaging and we're using 5 of our trials, that's 90 divided by 5, we end up with 18 trials to give to the classifier. Once you get over 15, this obviously dramatically drops. And now you can't divide 90 by 20, so we end up with 3 pseudotrials or 3 averages with some remainder. And this is the case for the whole of the right-hand side of this graph, which explains why in this case the classifier is performing poorly. Now, just really quickly to point out, we're not generating spurious results here with our averaging. So this is a data set where we simulated no effect, so it's just random. And you can see here that we're not increasing our decoding across our pseudotrial sets. there is an increase in the standard deviation, which we often see by increasing the number of trials per average. But you can see here that the t-score is very low and our accuracy is hovering around 50, 51. The crucial thing to point out here is that this result relies on the fact that we're creating multiple pseudotrial sets. And all that means is that we are randomly selecting trials and allocating them into our pseudotrials, and we do that 100 times. So we use random variations of all of the trials 100 times per participant. And therefore each point on here is the average of 100 different random pseudotrial iterations. And the main reason for doing that is just to make sure that there's no random combination of trials that gives us a specific effect that we wouldn't find with a different set of trials. And just to show you what this would look like if we didn't do that on a slightly smaller simulation, what you can see here is obviously that as you start to increase the number of trials per average, there's only a set number of results or decoding accuracies that you can have, and really there's no benefit to averaging it anymore. Your t-score just dramatically drops off. So just to bear in mind that this result is based on the premise of randomly allocating trials to pseudotrials over 100 iterations in this case. So you might be thinking, what about other classifiers? So we tried it on SVM and LDA, just showing you SVM here on the left. So what you can see, as with naive Bayes, you do have this initial jump, slight jump in this case in the t-score, when you go to averaging 2 trials. And of course, again, you see this dramatic increase in the standard deviation as we increase the number of trials per average. But really, in the case of SVM, the benefit is minimal once you have used more than a few trials per average. Another difference here is the drop-off is less severe when we've gone over using half the number of available trials. And this indicates that SVM is less sensitive to having fewer trials available than the naive Bayes was. Similarly, for the LDA, you can see actually we have this general increase in the t-score across time with a slight blip around over 15 trials. But again, the increase in t-score is not huge because again we're increasing the standard deviation as we increase the number of trials that we include in our average. The other thing that we can do is something called resampling, which, as you would imagine, just means using each trial more than once in your pseudotrials procedure. So what we wanted to see is if this would further help our classification. And on the left, you have the example I already showed you with no resampling. And on the right, a resampling of 2. So each trial can be used twice in 2 different pseudotrials. As you can see, the only real effect here, at least in the t-scores, is the stabilization in the sense that there's less jumping up and down after 15 and 20 trials per average. You can see there is also a slight jump in the standard deviation in the middle of the graph. However, really there's not much benefit in this case to doing extra resampling other than to stabilize the effect in the t-scores. The same is true even if you push the resampling up to 5, so using each trial in 5 pseudotrials. Again, there's not a huge benefit to doing that for the SVM classifier. And just to point out again, the difference between these 2 graphs is just the number of trials that we put into each condition. So on the left, if we're using each trial once in a pseudotrial and we have an average of 5, that is 90 available trials into 5 goes 18. However, if we can use each trial an additional 5 times, we can now have 90 trials going into our pseudotrial. And this is the difference between the data going into these graphs. Now, of course, there is a huge space that you can check this across. And what you can see here is, again, we've got our mean decoding accuracy, our standard deviation in the middle, and our t-score on the right. And if you were just trying to optimize for the maximum mean decoding accuracy, you might think that having quite a few trials per average and any number of trial resampling really of 4 would be the best place in this space. However, considering you're a t-statistic, you might actually be safer using roughly half of your trials, because including more trials, as we saw, increases the standard deviation. And again, as we pointed out, having only a low resampling value between 2 and 4 across the x-axis is sufficient to maximize your detection of the effects. Now coming on to a different classifier. As you can see here, we saw before, in this case, actually LDA seems to benefit from having few very clean trials, in the sense that it benefits from having many trials per average. However, again, the resampling doesn't really help you in terms of the t-statistic, and really you can be between 2 and 4 and have a good estimate of your effect. Then again, we come back to the naive Bayes, which had this dramatic drop-off as you include too many trials per average, and therefore because of that your t-statistic is optimal in the lower half of this space, and again with little influence of increasing the resampling value. So just to summarize, even a small amount of averaging appears to be helpful for all of the classifiers. However, certain classifiers, for example naive Bayes, suffer if you include too many trials per average. And resampling can help you to stabilize the effect, but it doesn't significantly improve on simply averaging, and you don't really need to use high values to maximize your sensitivity. So based on all of the data that we've looked at in our simulations, we conclude that if you create averages with roughly between 1/4 and 1/2 of your available trials per block, this is a good approach that seems to be fairly consistent, even taking into account different effect sizes and different classifiers, etc. Also, we would recommend only using a low resampling value, if any at all, between 2 and 4, but this shouldn't go above the number of trials per average. And obviously, there's a clear trade-off between these two things, so providing a classifier with fewer cleaner trials or higher noisier trials, and the optimal parameters do seem to vary quite a lot between different classifiers with different underlying effect sizes, and also with the number of trials that you have available. And much more of these parameters explored in the manuscript, which should be submitted soon. And that's all from me. Thank you for listening. If you have any questions or comments, here is my email and all of our Twitter accounts.